Hello everyone, welcome to our webinar on the simulation of a disk permanent governor in Autodesk Inventor. Today, we will delve into the fascinating world of electromagnetic simulations and explore how EMWorks Inventor software can be utilized to analyze and optimize the performance of a disk permanent magnet governor. Before we begin, let's go through the agenda for today's session. First, we will start with a brief introduction to the topic, followed by an explanation of the principles behind the permanent magnet governor. Then, we will discuss the permanent magnet materials available in EMWorks Inventor and how to define their coercivity direction. Next, we will dive into the magnetostatic analysis capabilities of EMWorks Inventor, including the various outputs that can be obtained. We'll also explore the relationships between torque, axial flux, and various design parameters such as air gap, magnet thickness, and inner diameter. Additionally, we will examine the magnetic field distribution inside the permanent magnet's yoke and conductor. Moving on, we will delve into the transient magnetic analysis features of EMWorks Inventor, enabling us to study dynamic effects and time-varying phenomena in the governor model. We will also discuss outputs such as transient torque, magnetic field distribution, current density, and heat flux distributions. Finally, we will conclude the webinar with a summary and address any questions you may have during the Q&A session. A disk permanent magnet governor is a crucial component employed in various mechanical systems, particularly in engines and machinery, to regulate and stabilize rotational speed. This innovative device harnesses the principles of magnetism to govern the velocity of rotating equipment effectively. In today's webinar, our focus shifts towards the finite element analysis, electromagnetic simulation of a permanent magnet governor utilizing EMWorks for Autodesk Inventor. FEA is a powerful computational technique that allows us to predict and analyze the behavior of complex systems by breaking them into smaller and interconnected elements. Moving ahead, the governing mechanism typically consists of a rotating disc mounted on the shaft whose speed needs to be controlled. This disc contains permanent magnets arranged in a specific configuration. As the shaft rotates, the magnets interact with other magnetic components to regulate the speed. As shown in the image, including the 3D model and the front view of the permanent magnet governor. Next, the disk permanent magnet governor operates on three fundamental principles of electromagnetism and mechanical dynamics. The first, permanent magnetism. The governor incorporates permanent magnets positioned on a disc-shaped rotor. These magnets generate a constant magnetic field without the need for an external power source. The magnetic field interacts with conductive materials in the vicinity and inducing eddy currents, which play a crucial role in speed regulation. Second, eddy currents. So, when the disk rotates within the magnetic field, it induces eddy currents in nearby conductive materials. These eddy currents generate their own magnetic fields, which interact with the permanent magnet's field, creating electromagnetic forces that act upon the rotor. Third, we have force balance. Now, the interaction between the magnetic field and the eddy currents results in electromagnetic forces that oppose the motion of the rotor. As the rotor's rotational speed increases, so does the strength of the eddy currents and the opposing electromagnetic forces. When the rotor slows down, the electromagnetic forces weaken, allowing the rotor to regain speed until a dynamic equilibrium is reached. So, engineers can carefully design several parameters to achieve optimal performance in a disk permanent magnet governor. First, we can go with the magnet configuration. The arrangement and strength of the permanent magnets on the disk are crucial. Engineers can optimize the placement and number of magnets to ensure the desired magnetic field strength and distribution for precise control. Other parameters could be air gap. Refer to the distance between the permanent magnets on the disk and the conductor rotor. Adjusting the air gap can affect the strength of the magnetic field and responsiveness of the control system. The torque generated in the governor is influenced by the air gap. Moving ahead, magnetostatic analysis in EMWorks Inventor is used to understand and analyze the behavior of magnetic fields in engineering systems and devices under static or steady state conditions. The magnetostatic analysis provides valuable insights into the distribution of magnetic flux, magnetic field strength, and associated phenomena within the system. Some common outputs which includes are like force and torque calculation, inductance computation as well as the resistance calculation. We can also look at the temperature distribution, magnetic field energy, flux linkage, current distribution, and many more. So with this, we will begin the analysis and we'll look at how EMWorks Inventor offers a wide range of permanent magnet materials that can be utilized in the simulation. As shown in the figure, the analysis of the disk permanent magnet governor requires a material library, and each material has its own unique material magnetic properties, which can be specified and accounted for during the simulation process as per the user need. Apart from the magnetic material setting, the next thing is to defining the coercivity direction, which is an essential step when working with permanent magnets in the FEA software. The coercivity direction represents the orientation of the magnetic field within the magnet material. So, using EMWorks Inventor, it provides various options for specifying the coercivity direction such as Cartesian, cylindrical, and spherical coordinates, allowing user for accurate representation of the magnetic field distribution. Let's begin with the analysis results. The image on the slide depicts a graph showing the relationship between the torque generated by the disk permanent magnet governor and the air gap distance between the permanent magnets and the copper conductor rotor. The x-axis represents the air gap distance, while the y-axis represents the torque value. As the air gap distance increases, the torque generated by the governor tends to decrease. This is because a larger air gap reduces the strength of the magnetic field experienced by the conductor rotor, resulting in a weaker eddy currents and lower electromagnetic forces opposing the rotor's motion. A smaller air gap leads to a stronger magnetic field, increased eddy currents, and higher torque values. So, optimizing the air gap distance is crucial for achieving the desired torque and performance characteristic for the governor. If the air gap is too small, it can lead to excessive torque, potentially causing mechanical stress or wear. On the other hand, if the air gap is too large, the torque may be insufficient to provide adequate speed regulation. Therefore, engineers must carefully select the appropriate air gap distance based on the specific requirements of the application, such as the desired speed range, load conditions, and material properties. Next, the image on this slide illustrates a graph depicting the relationship between the axial flux density and the air gap distance in the disk permanent magnet governor. The x-axis represents the air gap distance, while the y-axis represents the axial flux density, which is the density of magnetic flux lines along the axis perpendicular to the disk surface. Understanding this relationship between axial flux density and air gap distance is crucial for optimizing the design and performance of the governor. As the air gap distance increases, the axial flux density increases due to the weakening of the magnetic field strength. This relationship can be utilized to select the appropriate air gap distance that achieves the desired axial flux density required for efficient operation of the governor. Same, a higher axial flux density can lead to stronger eddy currents and electromagnetic forces, resulting in improved speed regulation. However, it is very important to balance the axial flux density with other design considerations such as any mechanical constraints, material properties, and overall system performance. Moving ahead, we have the next image on this slide shows a graph illustrating the relationship between the axial flux density and the thickness of the permanent magnets used in the disk permanent magnet governor. The x-axis represents the magnet thickness, while the y-axis represents axial flux density. Now, the thickness of the permanent magnet plays a significant role in determining the axial flux density, the overall performance of the governor as well. As the magnet thickness increases, the axial flux density initially increases due to the increased magnetic flux generated by the thicker magnets. However, beyond a certain point, further increasing the magnet thickness may not result in substantial increases in axial flux density due to saturation effects or other design limitations. By understanding these relationships, engineers can optimize the magnet thickness to achieve the desired axial flux density while considering factors such as cost, weight, and physical constraints. Thicker magnets may provide higher flux densities, but can also increase the overall size and weight of the governor, which may not be desirable in certain applications. On the other hand, excessively thin magnets may not generate sufficient flux density for efficient operation. Moving on to next slide. The image on this slide represents a graph showing the relationship between the axial flux density and the inner diameter of the permanent magnets used in the disk permanent magnet governor. The x-axis represents the inner diameter of the magnets, while the y-axis represents the axial flux density. Now, to understand the importance and its impact, as we can see, the inner diameter of the permanent magnet is an important design parameter that can significantly impact the magnetic field distribution and the resulting axial flux density. As the inner diameter increases, the axial flux density tends to decrease due to changes in the magnetic circuit and flux leakage effects. However, optimizing the inner diameter is crucial for maximizing the axial flux density while ensuring that the overall design meets performance requirements and practical constraints. A smaller diameter generally leads to higher flux densities, but it may also increase the complexity of the mechanical design or introduce other limitations. So here again, engineers must be careful, consider the trade-offs between maximizing axial flux density and other design factors such as manufacturing feasibility and cost consideration, of course. The impact of the inner diameter on the magnetic field distribution and flux density should be analyzed in conjunction with other design parameters to achieve an optimal balance for the specific application. Moving on, the image on this slide shows a visual representation of the magnetic field distribution inside the permanent magnets and the permanent magnet yoke of the disk permanent magnet governor. The color scale or contour lines represents the strength and distribution of the magnetic field within these components. So understanding these magnetic field distribution within the permanent magnets and the yoke is essential for evaluating the performance and efficiency of the design. This distribution provides insights into the magnetic flux paths, potential saturation regions, and areas where magnetic field leakage or inefficiencies may occur. By analyzing the magnetic field distribution, we can identify potential areas for improvement or optimization. For example, if the distribution shows a region of high magnetic field concentration or saturation, adjustment to the magnet configuration or material selection or geometric design may be necessary to improve the magnetic circuit, which in turn reduce losses. EMWorks Inventor allows for detailed visualization and analysis of these magnetic field distributions, enabling engineers to evaluate different design scenarios and make informed decisions to optimize the governor's performance and efficiency. Moving on, the next slide depicts the magnetic field distribution inside the conductor of the disk permanent magnet governor. The magnetic field distribution inside the conductor is a critical aspect that influences the generation of eddy currents and the resulting electromagnetic forces acting on the rotor. So these electromagnetic forces are responsible for opposing the rotor's motion and regulating its speed. So by understanding the magnetic field distribution within the conductor, we can optimize the interaction between the magnetic field and the conductor material. This knowledge can guide us the selection of appropriate conductor materials, geometric design, and other parameters to enhance the efficiency of eddy currents generation and overall performance of the governor. So again, EMWorks Inventor software provides detailed insights into this distribution, allowing engineers or researchers to visualize and analyze the magnetic field behavior within the conductor, and of course this information can be used to identify potential areas for improvement, such as reducing magnetic field leakages or optimizing the geometry for better electromagnetic force generation. Moving on, next we have transient magnetic analysis in EMWorks Inventor, which is a powerful feature that allows engineers to study dynamic effects and time-varying phenomena in the governor model. Unlike magnetostatic analysis, which focuses on steady-state conditions, transient magnetic analysis captures the time-varying nature of magnetic fields and their associated effects. By accurately simulating time-varying magnetic fields, engineers can analyze phenomena such as magnetic hysteresis, eddy currents, and electromagnetic transients within the governor system. This analysis provides valuable insights into the dynamic behavior of the governor, enabling engineers to understand and optimize its performance under various operating conditions. Some common outputs obtained from transient magnetic analysis include induced voltage, which is like the induced voltage in conductive materials due to the time-varying magnetic fields, which is crucial for understanding the generation of eddy currents. Other output could be temperature distribution, magnetic field energy, flux linkage and inductance, time-dependent distribution of magnetic flux density and magnetic field strength, time-dependent forces, transient torque, which is experienced by the rotor, eddy currents and losses within the conductive material, as well as the associated power losses which impact the efficiency and thermal performance of the governor. So in short, transient magnetic analysis is crucial for understanding the dynamic behavior of the disk permanent magnet governor and optimizing these for specific applications. So transient magnet analysis enables the evaluation of the governor response to transient events such as load changes, startup condition, or fault scenarios, ensuring that the design meets the required performance and reliability standards. So moving on, the image on this slide represents a graph or plot showing the transient torque behavior of the disk permanent magnet governor for a specific air gap distance of 1 mm. The x-axis represents time, while the y-axis represents the torque value. The graph illustrates how the acting torque on the rotor varies over time, providing valuable insights into the governor's response to various operating conditions and transient events. By simulating such visualizing transient torque characteristics, engineers can evaluate factors such as startup torque, steady state torque, transient response, any sort of overshoot, and settling time. So by analyzing these torque characteristics, we can also get the insights about the optimization, which is air gap distance, magnet configuration, material properties, or many other parameters. Next, we have the image on the slide, which shows a visualization of the transient magnetic field distribution inside the permanent magnets and the magnet disk. Studying the transient magnetic field distribution provides insight into the time-varying behavior of the magnetic field within the governor. This analysis is crucial for understanding how the magnetic field evolves and changes over time, as well as the dynamic interaction between the magnet as well as the disk and the other components. So as a researcher or engineers, what we'll visualize here is we try to identify the regions of magnetic field concentration or saturation that may vary over time. Other parameter could be analyze the dynamic flux paths and magnetic circuit behavior, which can impact the generation of eddy currents and resulting electromagnetic forces. Looking at this field distribution, we can also evaluate the potential of magnetic field leakage or interference with nearby components, enabling appropriate shielding or design modifications. So EMWorks Inventor enables detailed visualization and analysis of these transient magnetic field distribution, providing engineers with a powerful tool for identifying potential areas for improvement and optimizing the design for dynamic performance and reliability. Similarly, we can also visualize the current density distribution inside the conductor of the disk permanent magnet governor. This distribution is directly related to the eddy currents induced within the conductor due to the time varying magnetic field, and again by simulating the eddy current distribution we can identify the regions of high current density which may contribute to excessive heating or power losses, allowing for optimization of the conductor. We can also analyze the uniformity of current distribution, as non-uniform distribution can lead to uneven force generation and potential imbalances or vibrations. We can also evaluate the impact of design parameters such as magnet configuration or air gap distance on the current density distribution and the resulting magnetic forces. And finally, we can also optimize the current design for improved efficiency and performance by minimizing current crowding or ensuring uniform current distribution. So this optimization can lead to improved efficiency, reduced power losses, and enhanced overall performance of the disk permanent magnet governor. Next, we have this results shown for the heat flux distribution inside the connector of the disk. Understanding the heat flux distribution is crucial again for evaluating the thermal performance and identifying potential hotspots within the system. We can find out the region with high heat flux, which may lead to localized temperature rises or potential thermal issues. We can also look at the heat dissipation capabilities of the conductor, material, and geometry, which enables optimization for improved thermal management. We can assess the impact of design parameters as well as optimize the conductor design and material selection to balance thermal performance with other design consideration. So this can lead to improved reliability, extended service life, and enhanced overall performance by mitigating potential thermal issues or overheating. So in conclusion, the key points and takeaways from the webinar highlighting the value and importance of finite element analysis using EMWorks Inventor for simulation and optimization of disk permanent magnet governors. The FEA approach, coupled with magnetostatic and thermal analysis, provides valuable insights into the performance, reliability, and thermal behavior of the governor under various operating conditions. These insights enables engineers to make informed decisions, validate their designs, and optimize the governor for specific applications. EMWorks Inventor serves as a powerful tool for design validation, optimization, and performance evaluation. By integrating magnetic, thermal, and mechanical aspects into a comprehensive simulation framework, engineers can develop innovative solutions, improve performance, and enhance the reliability of the governor. So the ability to analyze and visualize various aspects that we have seen in today's webinar of the governor's behavior, which could be magnetic field distribution, current densities, heat flux, and any sort of transient phenomena, empowers engineers to identify potential issues and areas for improvement. This knowledge can be leveraged to optimize design parameters, material selection, and thermal management strategies, ultimately leading to more efficient, reliable, and high-performing disk magnet governors. Here are the references for today's presentation, and we are at the end of the presentation and opens the floor for a question and answer session. During this session, attendees can ask questions, seek any sort of clarification, or raise their concern related to the simulation of disk permanent magnet governors using EMWorks Inventor. And thank you so much for your attention throughout this webinar. Thank you.